Okay, well, yeah, happy Friday. It's week 5 Friday, which means we are halfway through the quarter. I don't know if, again, I can't tell if this quarter is dragging on or if it's like it's a little bit of a surprise that it's already week 5 or the end of week 5. I'm not sure. Um, so yeah, I guess we're halfway done. Um, yeah, all right. Let's talk about what we saw on Wednesday. On Wednesday, we said there's something that there's a limiting distribution that if we apply if we let a Markov chain run for long enough, that it might, that it will approach its limiting distribution, basically the distribution in the limit. And we looked at, some properties of Markov chains, and we said, if it's ergodic, which means, it'll be ergodic if it's aperiodic and irreducible, and all sorts. We covered those definitions on Wednesday, and we said if it meets these criteria, then it will converge to the limiting distribution and the stationary distribution. And so, here we can show that if you take the distribution at time n, which is pi super n, okay, if you take pi super n and you multiply it by the transition matrix, okay, then that will give you the probability distribution at the next step, at time n plus 1, which will be pi super n plus 1. And if you continue multiplying the current distribution by the transition matrix P, it will converge to the stationary distribution, as long as that chain is ergodic. Okay, so let's look at this transition matrix. Okay, and if this is our transition matrix, it has stationary distribution 0.75, 0.25. And what we'll see is that if I just keep multiplying my current distribution pi super n by my transition matrix P over and over and over again, it will approach the stationary distribution pi. Oh, you know what? Let me give you today's first quiz answer. Today's first quiz answer is B. B as in bear. B is our first quiz answer for today. B. My lighthouse. Okay. All right. So here I've got a distribution. We're going to start off with everybody at state 0. So we've got our distribution is 1, 0. Between the two states, we're going to start off, our current distribution is 1, 0. And if I multiply by the transition probability matrix, then at the next step, my probability distribution will be 0.8, 0.2, right? So we can, if I do 1.0 and I multiply by this, then I'm just taking kind of basically the first row, right? 1 times 0 plus 1 times 0. And I'm going to get 0.8, 0.2. And that's going to be the distribution at time n plus 1, the distribution pi at time n plus 1. And so if I take that 0.8, 0.2, and I multiply it by the transition probability matrix, then this is what I'm going to get. 0.8 times 0.8 is 0.64, plus 0.2 times 0.6, which is 0.12, 0.64 plus 0.12 is 0.76. And then if I do 0.8 times 0.2, which is 0.16, plus 0.2 times 0.4, that's going to be 0.08. 0.16 plus 0.08 is 0.24. Okay, so this is the distribution at the next time step. And then if I take that distribution, 0.76, 0.24, and I multiply it by the transition probability matrix again, this will be the distribution that I get, 0.752, 0.248, right? And if I keep multiplying by this, we can see that, well, maybe it'll approach the stationary distribution. And so that's what I've done here, okay? So I've done that in R. I created the transition probability matrix P in R. And here's my initial distribution. We've got distribution 1, 0. and I'm going to take x and I'm going to multiply it by p. So I'm going to get, when I take 1, 0 and I multiply it by p, I get 0.8.2. If I take this, and I've updated x accordingly, and if I take 0.8.2 and I multiply it by p again, I'm going to get 0.76.24. And again, I've updated x accordingly. And if I take 0.76.24 and I multiply it by p again, I get 0.752.248. Okay, which is exactly what we've shown here. And so I can take this and I can just run a loop. All right, so I'm going to just start off with the distribution at 1, 0. And here I'm going to just multiply by the matrix P. I'm going to do this 1,000 times. And then, I ask, well, what is x? Each time I'm doing it, I'm updating x. And so after 1,000 iterations, we can see, oh yeah, x is equal to our stationary distribution, 0.75, 0.25, right? So that's just kind of applying the transition matrix, 1,000 times, and we converge to our stationary distribution here. Okay, and it works even if I start off with a different distribution. So here I started off at 0, 1. Okay, now everybody is at the other state. Okay, and after applying the transition matrix one time, my distribution is 0.6, 0.4. And then I apply it again, and I get 0.72, 0.28. And I keep applying it, right? And it changes. And again, I'm going to do the same thing. Again, I start with a different distribution, but I'm going to apply the transition matrix, say 1,000 times. And after 1,000 iterations, I end up getting the same stationary distribution of 0.75, 0.25, which we said, is our limiting distribution and our stationary distribution. Limiting distribution meaning, what happens to the distribution, after letting the chain run for a long time. So here I've let it run for basically 1,000 iterations. At least this is not actually letting the chain run where we're looking at the probability distribution after 1,000 iterations. So after doing that, we see the distribution here is, this is our limiting distribution, and this is our stationary distribution. Okay, is that all right? All right, so a lot of you had me as a teacher for 102A. Maybe some of you did not, but one of the homework assignments from 102A was you had to write kind of some code to simulate board movement on Monopoly. Okay, and in that assignment, I had you do object-oriented programming, and you had to kind of write, you had to read the rules and program the rules into the game, and then you would record where the players landed up. Okay, there's another approach, another strategy that can be used for figuring out board probabilities, and that would be using the Markov chain approach. Okay, and so what you can do is instead of coding up the rules, you can create a giant transition probability matrix. There are 40 spaces on the board, so you would create a 40 by 40 transition probability matrix. Okay, and the first space would probably represent go, and it would say, what is the probability you start at go and end up at any of the other 40 spaces. Okay, and so if you start at go, then if you only implement the dice and no other rules, then you'd say, okay, well, the probability of rolling a 2 on the dice is 1 out of 36. And so, you're kind of, the first row in that transition probability matrix would say, okay, if you start at go, we're going to say you can't go 1 space, but you can go 2 spaces with probability 1 out of 36. And then you can end up 3 spaces away with probability 2 out of 36, because out of the 36 possible dice roll combinations, there 2 will add up to 3, and so on and so forth. And so you could end up 7 spaces away with a probability of 6 out of 36, and you can end up 12 spaces away with probability 1 out of 36. Okay, and that's just the dice. But technically, the probabilities are not going to be this because there's different cards that move you around and different rules that also move you around. And so technically, even if you start at go, it's possible to end up at boardwalk because you could land on a chance space, and then you can draw the boardwalk card and you can end up at boardwalk, right? And then technically, if you roll doubles, you get to roll again. And so you know, the probabilities get, you know, a lot more complicated. But given that you've started your turn at, you know, any one space, you could figure out the probabilities of ending up at any of the other spaces on the board. Okay, and so, you know, that 40 by 40 matrix would be rather difficult to kind of figure out. You have to, every single probability, you kind of have to think through the rules there. But it can be done. And once you've developed that kind of large transition probability matrix, you can then seek out what is the stationary distribution of this big matrix. Okay, and so so I've got a couple links that you could check out if you're interested, of people who take this Markov chain approach to kind of figure out the board probabilities of all the spaces on the Monopoly board. Okay, so it's kind of an interesting thing. These are, well, I don't know. I think it's interesting. Some of the student feedback that, you know, from 102A is always like, I used to like Monopoly, but now I have, you know, terrible memories of this. I've ruined the game Monopoly for them. So my apologies. I still have fun playing the game. But anyway, I guess I like board games in general. All right. Okay. So yes, what we said on Wednesday was that if we have a Markov chain and it's got this transition probability matrix P, and as long as the Markov chain is ergodic, it will eventually reach its stationary distribution pi. Okay, and once it converges to the stationary distribution, then the values that it generates from that point on will come from the stationary distribution. Right. So I'm going to introduce the Metropolis algorithm, or I should say like the light version of the Metropolis algorithm, or a junior version of the Metropolis algorithm. And that's going to give us a way to design the transition probabilities of a Markov chain so that the stationary distribution of this Markov chain will be equal to whatever target or desired distribution that we want. Okay, because the overall goal is, how do we generate samples from some distribution? Okay, and we've already covered a lot of techniques like the inverse CDF and rejection sampling and stuff like that. But we want to see, well, can we use this Markov chain approach and generate samples from some distribution that we want? And the answer is yes. And the Metropolis algorithm is one way to achieve this. Okay, and so again, today's introduction is going to be like is just a discrete case, and it's going to be kind of like the simplified version. And next week, what we'll do is we'll further develop this so that we can generate values from a continuous distribution and things like that. Okay, so the example I'm doing today comes straight from this textbook, Doing Bayesian Data Analysis. Okay, and I've kind of just taken lifted the example in that textbook and just kind of put it straight into the notes here. And so anyway, make sure you do your reading. And I'm working on your next homework assignment, so that should get created, and I hope it will be informative in how this stuff works. Okay. How is your current homework assignment coming along? It's okay. We're getting a handle on all of these sampling techniques, maybe. All right. Okay. If so, then that's a success. All right. All right. So imagine a nation consisting of islands in a chain. So we've got some kind of island nation. And then a politician, I know we've had enough of politics right now, but a politician travels from island to island trying to stay in the public eye. Okay. And at the end of the day, this politician has to decide whether or not to stay at the current island or move to the island to the west or move to the island to the east. Okay. All right. And so those are the only three possibilities. He's either going to stay at the current island, he's either going to go one island to the left or one island to the right. Okay. And those are the only possibilities. And his goal is to visit all of the islands proportionally to their relative population, right? So that at the most populated islands, he's going to spend the most time, and at the less populated islands, he's going to spend less time, okay? This nation doesn't use the Electoral College where random places seem more important than others, but okay, well, anyway. So it's going to be the biggest islands he wants to visit the most, the small islands he's going to visit less often, all right? But he doesn't know the total population of the island chain, but we are able to find out the population kind of the island he's currently on and the population of the adjacent island. This seems like a weird statement to put in here, but we'll see how this becomes relevant later on, okay? So we don't know the total population of the island chain, but we need to know the population of the current island and the population of the adjacent island. Adjacent islands, I guess. All right, and so this is the algorithm. This is the algorithm that this politician is going to use for visiting the island, okay? And this algorithm works, okay? So each morning he flips a coin, okay? So he flips a coin. If it lands heads, he's going to propose the island to the west. If it lands tails, he's going to propose the island to the east, all right? And then whatever island he proposes, he's going to call and see what is the population of that proposed island. And he's going to compare it to the population of his current island, okay? If the proposed island has a larger population than the current island, he's definitely going to go there, okay? He says, I got to go there, right? I want to make sure these people see me. But if the proposed island has a smaller population than the current island, then he's going to go to that island probabilistically, okay? And that is his probability of moving there is going to be the probability of the proposed island divided by the probability of population of the current island, okay? And so if the proposed island is half the size of the current island, he will go there with probability of 50%. If the proposed island is, say, 80% of the size of the current island, then he'll go there with probability 80%. Okay, so that's how he's going to decide whether or not to go to the proposed island. Okay, and so in order to go there probabilistically, then he's going to select a random uniform value, and if it's less than p move, then he'll move to the proposed island. And if he doesn't move to the proposed island, he's going to stay put at his current island. And that's the algorithm, okay? This is basically like a junior version of the Metropolis algorithm, and the system works, okay? And so in the long run, the probability that the politician is on any one of the islands exactly matches the relative population of the island, okay? So, so let's do this with a slightly more concrete example. So let's say, and this will work for any sized island nation, okay? So in our example, just to kind of hammer down some real numbers, we're going to say there's 7 islands, okay? But you can have 100 islands in the nation, okay? And this would still work, okay? So let's just say we have 7 islands, and the islands are numbered from island 1 to island 7, okay? And we're going to say that the relative populations of each island is proportional to their island number. So island 1 has a population that is 1/7 the size of island 7's population. Okay, so here I listed this out. We got island 1, 2, 3, 4, 5, 6, 7. Island 1 has a population of 1,000. Island 7 has a population of 7,000. Okay, so small island nation, I guess. Okay, and so the target distribution, which needs to add up to 1, and this is what we want our stationary distribution to be, is going to be 1 out of 28 for island 1, probability 2 out of 28 for island 2, 3 out of 28, all the way up to island probability 7 out of 28 for island 7. Okay, 7 out of 28 is 1/4. Okay, and so these probabilities add up to 1, and this is what we want for our stationary distribution. This is our target distribution. If we want to visit, the politician wants to visit the islands with kind of this relative probability across the different islands here. Okay, so that's going to be our stationary distribution. That's what we want. Or I guess what I should say is this is our target distribution, and we want our stationary distribution to be equal to our target distribution. Okay, so these are the rules. Again, we flip a coin. If it lands heads, we propose the island to the left. If it lands tails, we propose the island to the right or the east. And then if the island is bigger, we will go there for sure. If the proposed island is smaller, we go there probabilistically. All right, so let's say we start at island 4. If we start at island 4, what's the probability that we're going to go to island 5? Okay, so in order to go to island 5, we have to flip the coin, and it's got to land tails. And that means we will propose island 5 with probability 0.5. Okay, if the coin lands tails, we'll propose island 5, and that's going to happen 50% of the time. And if we propose island 5, we'll go to island 5 with probability 1 because island 5 has a bigger population than island 4. So we go there with 100% probability. So the total probability of moving from island 4 to island 5 is going to be P45. And that's the probability of proposing island 5 multiplied by the probability of moving to island 5 given that island 5 was proposed. So that's going to be 0.5. That's the probability of proposing it. And if we propose island 5, what's the probability we move there? That's 100%. So the total probability is 0.5. Okay, what about going the other way? Okay, what's the probability that we go to island 3? Okay, so again, we flip the coin, and if it lands heads, we will propose island 3. So we propose island 3 with probability 0.5. If we propose island 3, we move to island 3 with probability P move, which is the proposed probability divided by the current probability. That's going to be the proposed island in our target distribution is 3/28 versus our current island's probability in the target distribution, which is 4/28. So 3/28 over 4/28, we're going to move there with probability 3/4. Or in other words, island 3's population relative to island 4 is 3/4. So the total probability of moving from island 4 to island 3, P43, is going to be the probability of proposing island 3 multiplied by the probability of moving to island 3 given that island 3 was proposed. So we propose island 3 with probability 0.5. And if we propose it, the probability of moving there is 3/4. So the total probability of moving to island 3 is going to be 0.375, okay, or 3/8. 1/2 times 3/4 is 3/8, or 0.375. So what's the probability that we stay at island 4? Okay. So what's the probability he stays at island 4? So he's going to stay at island 4 if he proposes an island but doesn't go there, right? So we've got to propose island 3 but not go to island 3. Or we can propose island 5 and not go to island 5. So what's the probability that happens? Okay, we propose island 3 with probability 0.5. And we go to island 3 3/4 of the time, which means we won't go there 1/4 of the time. Okay, we propose island 5 half the time, and we go there 100% of the time. So the probability we don't go there is 0 if we propose island 5. So the total probability that we will stay at island 4 is going to be 1/2 times 1/4 or 1/8, 0.125. Okay. All right. And so, so my three probabilities going from island 4 to island 5 is 1/2. Island 4 to island 3 is 3/8 or 0.375. And staying at island 4 is 1/8 or 0.125. Okay. And so I can start to fill out my transition probability matrix. Okay. So I've got 7 islands. And so I've got a big 7 by 7 transition probability matrix. And this is going to be the row for row 4. What is the probability of starting at island 4 and ending up at any of the other islands? Well, it's impossible to go to island 1 or island 2 if I start at island 4. And it's impossible to end up at island 6 and 7 if I start at island 4. But these are the probabilities I end up at island 3, island 4, and island 5. Okay, and we went through the math on the previous slides. All right, is that okay? Okay, what about if we start at island 1? Okay, if I start at island 1, what's the probability I go to island 2? Well, I flip the coin and I have to propose island 2, so that happens with probability 1/2. And if I propose island 2, I will go there for sure because island 2 has a bigger population than island 1. Its population is 2,000 versus island 1, which is 1,000. So I will go there for sure. So my probability of going to island 2 is 0.5. If I start off at island 1, you know, there's no island to the left. So I'm going to just pretend we're going to say, like, can I go to the left? And we're going to, what's the probability I go to island 0? Okay, island 0 doesn't exist. So we can treat it like it has a population of 0. Okay, so that's going to be, what's the probability I go to island 0 from island 1? Well, it's the probability of proposing island 0. So that's going to happen with probability 1/2. And what's the probability of moving to island 0 if we propose it? Well, we're not going to go there because it doesn't exist. So the probability of going to island 0 is 0. And so the probability that I stay at island 1 is going to be 1/2 because, you know, all three numbers have to add up to 1. So I'm going to not move to island 0 with probability 0.5, and I will not go to island 2, you know, with probability 0 here. And so, so the total probability of staying at island 1 is 0.5. So if I put that into the transition probability matrix, I will get 0.5, 0.5. So starting at island 1, I will stay at island 1 with probability 0.5. And starting at island 1, I will go to island 2 with probability 0.5. And everywhere else, it's not possible for me to kind of end up in that location, because we're either going to go to the island to the left or the island to the right or stay put. Okay. I don't know if I need to go through all of these things, but I did it for islands 2 and island 7. Okay. So island 2, the probability I go to island 3 is 1/2. It's just, if I propose anything to the right, I'm going to go that way, right? And then the probability I go to island 1 is going to be 1/2 times 1/2, 0.25, and the probability I stay put is going to be 0.25. Okay. If I start at island 7, right? So island 7 is kind of the eastmost island. What's the probability I go to island 8? Well, island 8 doesn't exist, so we go there with probability 0. Okay. What's the probability I go to island 6? Okay. Well, the probability of moving to island 6, if it's proposed, is going to be 6 over 7. And then so the probability of going there is I first have to propose it, multiply by the probability of going there, which is going to be 1/2 times 6/7. So that's going to be 3/7. Okay. And so I get 0.4285. Okay, that's probability 76. And then, you know, all of these things have to add up to 1, but, you know, we can go through the math here. And the probability that I'm going to stay at island 7 if I start at island 7 is going to be 4/7. Okay, 0.5714. All right, and so if I just kind of follow the rules and I fill out the entire probability matrix, this is what we're going to get. Okay, so this is our kind of total transition probability matrix, and I put it both in fraction or decimal form here. Okay, so I think I computed the math for this row. these two rows and this row, and then, you know, it's not too hard to figure out the other rows either. Is that all right? All of these probabilities. And so what we see is that the probability of going, you know, if you start at island 1, what's the probability you end up to the island to the right? Because the populations keep getting bigger, this side is always going to be 0.5 because that's the probability of just proposing there. And if you propose that island to the right, you're going to go there. Okay. And then going to the island to the left is basically, you know, this is relative to your current island multiplied by the probability of proposing it, which is 1/2. Okay, let me give you your second quiz answer, right? Okay, second quiz answer is E. E as in elephant. E as in elephant is the second quiz answer. Page 11. Okay, so let's request to look at page 11. This one. So, so this is just kind of the silly example that we're using to kind of frame our our talk of the Metropolis algorithm, which is that the politician is oh, I'm sorry, probability of island 1 to island 1. Okay, not page 11. Okay. All right, probability of island 1 staying at island 1. Okay, so we will stay at the current island if we propose an island and don't go there. Okay, so we propose an island 0 and we don't go to island 0, right? So what's the probability I propose island 0? That happens with probability 0.5. And if I propose island 0, what's the probability I'm not going to go to island 0? Well, I'm not going to go to island 0 100% of the time island 0 is proposed. So every time, so I will propose island 0 if the coin lands heads, okay? So if it lands heads, I propose island 0. And if I propose island 0, I'm going to say, well, it doesn't exist, so I'm not going there. Okay, I'm going to stay put. So I'm going to stay put 50% of the time. It's technically the probability of proposing an island and not going there. So what's the probability I propose island 2 and don't go to island 2? I propose island 2 with probability 0.5, but then every time I propose island 2, I go there for sure. So the probability of not moving to island 2, given that island 2 was proposed, is 0. So the total probability of staying put at island 1 is 0.5. Okay. And so, you know, you can go through this, and this is your entire transition probability matrix. Okay. All right. So we have we've defined our Markov chain, right? A Markov chain is defined by its kind of transition probabilities, and so so we've defined our transition probabilities. And so let's say, what is the stationary distribution of this Markov chain? Okay. So we can find the stationary distribution by finding the left eigenvector of our transition matrix. Okay, so I've entered the transition matrix into R as matrix P. Okay, so I just row bind all of these row vectors. And I'm going to find the left eigenvector. Okay, so I'm going to take the transpose of P and find the right eigenvectors of the transpose of P. So I'm going to do right eigen of the transpose of P. Okay, and I ask, okay, and then what's the stationary distribution? Well, I'm going to transpose that right eigenvector back into a row vector, and I'm going to normalize it by taking the sum of the right eigenvector, because R's default behavior of eigenvectors is that the norm of it is 1, but not the sum. Okay, so it gives you a vector where the norm is 1. So if you square all the values, you get that. But here I'm going to normalize it so that the sum equals 1. Okay, so this is going to be my stationary distribution. So here's my stationary distribution: 0.0357, 0.0714, et cetera, et cetera, et cetera, 0.025. And we can see that it's the stationary distribution, because if I take the stationary distribution and I multiply it by the matrix P, I get back the exact same values, okay? Indicating that when I, because that's what we want. At the stationary distribution, after going through the transition matrix again, we want to get back the same distribution. We don't want any, we want everything to remain stationary. We don't want the probabilities to be changing, okay, at the stationary distribution. So the stationary distribution multiplied by the matrix P is still the stationary distribution, and we can see that all of these values are the same. Okay, and then so the next question is, all right, so this is the stationary distribution of this transition matrix that we've created. And the question is the stationary distribution equal to our target distribution, right? That was the whole point. We want to get, we want the stationary distribution to look like the target distribution. And so the target distribution is the probability distribution where the probabilities are proportional to the island populations. So we want our target distribution be, 1/28, 2/28, so on and so forth to 7/28. So my target distribution is going to be 1 through 7 divided by 28. And I can ask, is the stationary distribution equal to the target distribution? And R comes back and says, yes, that's true. Okay. And then we can actually check these values ourselves, right? So this last number, 7 out of 28 is 1/4, and we get that. And the next value, 6 out of 20 is 0.24, 0.21428. Okay, and that matches. If I go all the way to the island 1 out of 28 is 0.0357. So yes, our stationary distribution is equal to our target distribution, which is great. Okay, so we've achieved the desired outcome, that we've designed a Markov chain. Okay, just kind of following these silly rules back here. Okay, following these silly rules, we've developed a transition probability matrix, and the stationary distribution of this transition probability matrix is our target distribution. So mission accomplished there. All right, so here's just kind of a little diagram showing, what happens, right? So here we're going to say, let's start off with the politician being at island 4. Okay, so this is day 1. On day 1, he's at island 4, and we say, well, okay, where is he going to be tomorrow? Okay, where is he going to be tomorrow? And so he's only going to be at one of the islands, but we can come up with a probabilistic distribution. We can say, what's the probability he's going to be at island 3? What's the probability he's going to be at island 4? What's the probability he's going to be at island 5, right? So if we look at the transition probability matrix, he's going to end up at island 3 with probability 3/8. He's going to be at island 4 with probability 1/8. Island 5 with probability 1/2. So I multiply. So what I'm going to do is I'm going to kind of create a matrix, pi sub n, where each row is his probabilistic distribution at each day. So, so the first day, he's got 0 probabilities of being at islands, 1, 2, 3, 5, 6, 7, and 100% probability of being island 1. Okay, and then so I'm going to take that row and I'm going to multiply it by the transition probability matrix P, and I'm going to store that as the second row in my pi sub n matrix. Okay, so pi sub n on the second row is going to have this distribution. He's got a 0.375 probability at island 3, a 0.125 probability of being at island 4, and a 0.5 probability of being at island 5. Okay. And then we can say, okay, well, this is his probabilistic distribution at day 2. Where is he going to be at day 3? So we can take these probabilities and we can apply the transition probability matrix again, right? So we can say, well, what is the probability he's going to end up in island 6 on day 3, right? So the only way he can go from island 4 to island 6 in 2 days is if he flips heads twice, right? He's got to flip heads and he will end up at island 5. And then if he's at island 5, he's got to flip heads again and to end up at island 6. Okay. So the probability he's going to end up at island 6 is 0.25. Okay, what's the probability he's going to end up down at island 2? Okay, well, first he's got to end up at island 3. That happens with the probability of 3/8. And then what's the probability he goes from island 3 to island 2? Okay, if you look up the transition probability matrix, the probability of going from island 3 to island 2 is 1/3. Okay, and so the probability he's going to end up in island 2 after on day 3 is going to be 1/3 times 3/8, which is 1/8. Okay, and then everything else is going to be kind of a sum of, to end up at island 3, he's got to either, there's 2 ways to end up at island 3 on day 3. It's either he goes to island 3, goes from island 4 to island 3, and then stays put at island 3. The other way is he stays put at island 4 and then goes to island 3. Okay, and then there's a few ways to end up at island 4. We can go from island 4 down to island 3 and back to island 4. We can go from island 4 to island 5 and back to island 4. Or we could actually stay put at island 4 and stay put at island 4 again. So there's a few ways. So anyway, if you go through all of the ways that could happen, so this is going to be the total distribution for day 3. So being at island 2 is 1/8. Being at island 6 is 1/4. And then everything else is kind of a combination of all of the different things. So this is our distribution on day 3. And then we can kind of continue to apply this, and we can say, well, what is the probability? So if I multiply by the transition probability matrix, what's the distribution, probability distribution, where the politician will be after 3 days on day 4? And this is where we are. Okay. And we can just kind of continue this, and we can say, let's repeatedly multiply by the transition probability matrix just to kind of see where we end up. Okay. And so this is kind of the distribution on day 10, the probabilistic distribution of where the politician could be on the 10th day. And then just to kind of compare day 10 versus day 11, I kind of plotted these side by side, and we can see, okay, yeah, things are still, we haven't reached the stationary distribution. Things are still fluctuating. The probabilities of where we are at day 10 is a little bit different from the probabilities of where we are at day 11. And so, if I say, are all these things equal, R comes back and says, no, you get about a 5% difference with the relative difference between the day 10 probabilities and the day 11 probabilities. There's about a 5% difference. Okay, well, what about days 20 and 21? Okay, days 20 and 21, a bit more similar in distribution. Did things change much from day 20 to day 21? Ever so slight changes, okay? And the mean relative difference is about less than a 1% change for the probability distribution of day 20 and the probability distribution of day 21, okay? And then if I go to day 99 versus day 100, we can see, okay, at this point, it's becoming pretty stable, okay? R still says they're not all equal, but the difference between day 99 and day 100 is on the order of 10 to the -7. Okay, so it's a very, very small difference between the distribution at day 99 and the distribution at day 100. Okay, and so we're approaching kind of the stationary distribution, just after 100 days here. And so anyway, this is just kind of, I think it's pretty neat that we have a fairly simple algorithm to design this transition probability matrix. And this transition probability matrix, which defines our Markov chain, will have a stationary distribution equal to the target distribution that we want. Okay, and so that's kind of the very basic intro to the Metropolis algorithm. We'll formalize it a little bit further. We'll look at how some of this stuff works next week, and we'll further formalize it to apply to other distribution types, and then we'll generalize it more with the Metropolis Hastings algorithm. And then I think I've got a pretty neat application of this too. Okay, so we'll end here. Let me give you your last quiz answer for today. Last quiz answer is D. D as in dog. Okay, D as in dog is your last quiz answer for today. And yeah, and so we'll end here. Have a good weekend, you guys, and we'll see you guys on Monday.